Hey there, and how's it going? Welcome to lesson 3.3. 3.3 says this. I can draw an energy bar graph that shows energy transfer and storage during different kinds of physical changes. So definitely a mouthful there. If we toggle to our list, we're about halfway through the unit here, 3.3. And now let's go back to Notepad and get started. So let's go ahead and first kind of define the word energy. What does energy mean? Well, energy is kind of what I describe it as the stuff that makes things operate. So for example, if we have a pot of water here, you want to heat it up, what you have to do is either burn some wood, turn on your gas stove, and burn something to infuse this pot of water with energy. If you're into sports, then what you have to do is drink your Gatorade, right? Get your electrolytes, your sugars in there. You have to eat things like pastas for carbohydrates, meats, or other protein sources for protein, right? And again, our body literally burns food to give you energy. A final example is, for example, if you get into a car and you want to travel somewhere, we know that we have to fill the gas tank full of gasoline. The internal combustion engine then burns the gasoline, and in doing so, you're kind of transferring one type of energy to another, and that's what they mean by energy. So something that we've just established is that energy can transfer. It goes from form A to form B, whatever those forms are. So when you burn wood, it'll turn into heat. When you eat food, it'll still somehow turn into heat or expenditure through your body, right? So you start with one type, and the energy is used and transferred to another type. Energy is kind of like conservation of matter because we can either create or destroy it, we can just switch its forms. Something that we can specifically write about heat is that it moves from hot to cold. So notice there's a hot bed of colds and it's moving into the cold surroundings. The water is a little bit colder. So again, the heat moves from hot to cold. So let's go ahead, let's write that down for ourselves too. So heat moves from hot to cold. So in our chemistry class, what we're going to have to do is visually quantify heat transfer, and the way we're going to do it is using an LOL chart. So here on your right, something called an LOL, and we'll show why it's called an LOL. So if I highlight here, this O, and then this other thing here that kind of looks like an L, notice that we get the word LOL out of it. And this is just a fancy way of kind of quantifying and visually showing heat transfer. As we zoom in closer into the graph, we see that there are some very specific columns here at the top. So here it says E thermal, that's what that TH stands for. This is E phase, and this is E chemical. So something we can do is for now, we're going to kind of cross out the E chemical, and the two things we're going to really focus on is E thermal and E phase. So E thermal corresponds to specific values, and those values have to do with temperature. So what we're going to end up doing is drawing these bars into these pre-described locations. And depending on what the scenario given to us describes, we're going to have to try to kind of draw the amount of bars that are representative of that situation. So hot is going to be 4 bars. So that looks something like this. Room temp, 20 degrees for the thermal column will be 2 bars. It's going to look something like this. Cold is going to be 1 bar. So there's our 1 bar. And if something is described to be frozen, then we're going to draw half a bar, and that's going to look something like that. So E phase now corresponds to these values over here. And notice that we have three types of phases, right? That we learned about in the previous videos. Gas, liquid, solid. If a gas is described to us, then what we have to do in this column is draw in 4 bars here in the middle. So it'll look something like this. If we get a liquid, then we're going to draw 2 bars. It'll look something like this. And then if I get a solid, it's going to be 1 bar. It's going to look something like this. Notice at the top that it says initial and final. So this is kind of like your before, and this is your after. So we'll get a situation that describes some sort of thermal change, and we'll need to describe it first here, and then we'll have to show the change over here. The last thing I just want to mention is there's a circle in the middle. We haven't talked about that yet. And what goes in the circle is the system. It's the subject matter that we're talking about. So let's say that we want to describe the energy transfer of this pot here to our left. What I would say is pot of water is our system. And then the last thing you'll always have to decide is whether energy enters or leaves the system. You'll have one of these two choices. You'll either draw an inward arrow or an outward arrow. All right, so at first this totally seems like a ton of information, but I think once we start doing some problems, you'll kind of see how really easy it is to figure this out, okay? So here's our first problem. It says a hot cup of coffee is poured into a cup. It sits on a countertop for 2 hours and cools to room temperature. So there's our hot cup of coffee. All they've done is they've poured it out, and it's just been let to sit. Let's graph this out in this blank graph so we can visually see what's going on. So we'll call this temp versus time. Let's put our 2 key temperatures for water, right? Coffee is mostly water, 100 degrees C, 0 degrees Celsius. And about a quarter of the way up, we'll have to put 25 degrees Celsius. That is room temp. Let's say RT, room temp. So hot coffee is typically made with boiling water, and if it cools, we're going to start at 100. If it cools for 2 hours, we're simply going to have a downward slope until we hit room temperature here. So that's what we have to describe here now on our LOL chart. So what's our system? We could call it coffee. And our thermal to start, let's kind of double check what we need. What temp? Definitely 4 bars because it's hot to start, okay? So let's draw those 4 bars in. There's 1, 2, 3, 4. The phase, let's check that out. What do we need? Definitely a liquid, so 2 bars for phase. Let's put that in there. And now we've kind of come to a fork in the road. We have to ask ourselves, what is the final going to look like? So I have to ask myself, is the phase changing? Are we no longer a liquid? We still are. So for the phase is not going to change. We're going to put 2 bars down for phase. So that looks the same. But something I suspect will change is the thermal, right? We go down from hot, and I think I actually go down to room temp, right? So we're going to have to knock this down to 2 bars. So notice right now from left to right, we have less bars from left to right. We've lost energy from beginning to end. So which way should my arrow point? Am I gaining or losing energy? Well, the coffee's definitely losing energy. So we're going to make an outward arrow. And how many bars of energy? Well, we lost this one, and we lost that one left to right. So we could write down 2 bars lost. And there you go. You've just completed your first LOL chart ever. Let's now move to example 2 and take care of another one. So here's what example 2 says. Ice is taken out of the freezer and put onto a countertop. The ice begins to melt and eventually turns into a small puddle of water. Let's graph this situation. So again, we got to put a title. Temp versus time. Okay, let's put in our key temps. So 100 degrees Celsius. We'll put 0 here at the bottom, 0 degrees Celsius. And remember, about a quarter of the way up, you have to put 25 degrees Celsius. This is your room temp. All right, so ice, we know, freezes / melts at 0 degrees Celsius. So immediately I'm kind of drawn to this temperature here on the side. And I know that during a phase change, temperature does not increase or decrease. It stays the same. Remember, we hit a flat, it plateaus. So here's what my graph needs to look like. We're simply going to draw a flat line on the x-axis. So we'll try to make it a little bit thicker so we see it. But really, that's all we need, because a phase change is always flat on a heating curve, and that's what it should look like. Let's go ahead and let's label our LOL chart. So our system is the ice cube. Let's figure out our thermal. So let's go back to our reference sheet. So is an ice cube hot? No. Room temp? No. Is it cold? Sure. But is it frozen? That's definitely the best answer. So our initial is going to be a half for thermal. And now let's move back up to our reference sheet and let's ask ourselves, what should we pick for the phase? Is phase changing? Definitely is, right? And if a frozen ice cube melts, we're moving from a solid of 1 bar to a liquid of 2 bars. That's what constitutes the phase change. So let's go ahead, let's draw those in. So 1 bar there. Phase needs to change to 2 bars. So there's our liquid. And let's ask ourselves, is temperature changing at all in this graph? It's not at all. It's plateaued. It's flat at 0 degrees C. So our temp is still going to be a half bar for frozen. And here's the final question we need to ask ourselves. Do I have a net temperature or energy increase or decrease? Are there more bars on the left or on the right? Well, as I count them, the right definitely has more bars. So from the surroundings, this system has pulled in energy. We're going to give it an inwards arrow. And something we've noticed is that we've gained 1 bar. So this has been a lengthy video, and the last thing I want to leave you with is that this skill definitely looks like a lot at first, but practice truly makes perfect. The more you practice this, the more of these problems you see, the better you'll understand them, and you'll see that things start to repeat themselves. It's all in the practice. So when your teacher gives you the packet, go ahead and do all the problems. That's my best recommendation. That's how I got good at it and everyone else. And as always, have a great day, and we'll see you next time.